No. I need to open this. I should share my screen. Should I reclaim those? Let's see. Yeah. Oh, sorry. Nope, no, this one is. Sorry, so it swaps it for the Zoom link. Okay, let me try this. Oh my goodness. Okay, let me try again. Anyone have jokes? Okay. Yeah, I don't really know what to. There's usually a thing that says swap views, but I don't see it. So.
This is fine.
Yeah. Can I just leave the Zoom and rejoin?
Oh,
Oh, okay. Yeah. Is that going to do it?
All right, good. So the last speaker of the day is Fermi, post-quantum succinct arguments.
Thanks, Andrea. Thanks for bearing with me. Right, so this is post-quantum succinct arguments, breaking the quantum rewinding barrier. My name is Fermi Ma, and this is a joint work with Alessandro Chiesa, Nick Spooner, and Mark Zhandry. So let me start with a simple motivating question. Why are quantum computers a threat to cryptography? And to understand this a little better, let's go into how cryptographers formally prove security. So a typical crypto security proof can be broken down into two components. First, there's going to be some kind of computational hardest assumption. So this is something like hardest of inverting only function or hardest of factoring. And you couple this together with a security reduction. And what the security reduction should say is that any efficient attack on your crypto protocol implies a way to break the underlying hardest assumption. Right, so as long as you have faith in your underlying assumption actually being hard, then this tells you that your protocol is going to be just as secure. Okay, so with this picture in mind, let's revisit this question: why are quantum computers going to be a threat? And the sort of immediate answer is that Shor's algorithm is going to break a lot of the assumptions that we base modern crypto on, in particular factoring and discrete log. Right, so if we want post-quantum cryptography, which is classical cryptography secure against the possibility of quantum attack, then the absolute bare minimum requirement is that the underlying assumption must resist quantum attack. Okay, but fortunately, we have candid hard problems. A notable example is the learning with error problem from lattices. But a common misconception is that this is the only thing you ever need to consider when doing post-quantum cryptography. That post-quantum assumptions are, that's all you need, just plug one in and then you're post-quantum secure. And the reason that this is a misconception is that it's ignoring the other half of this equation, that the security reduction also has to be quantum compatible. So let me elaborate. Say you have a protocol and you've already proven security in the classical setting, but then you have to swap out your assumption for a quantumly hard assumption. And you're asking, is my resulting protocol post-quantum secure? Well, if you proved classical security, you likely wrote down a classical reduction. And what the reduction says is that any classical attack on the protocol can be turned into a corresponding attack on the assumption. But if you want to actually conclude quantum security, you need a quantum compatible reduction that says a quantum attack on the protocol turns into a quantum attack on the assumption. Okay, so what's the difference? Well, it turns out in many cases, classical reductions can be easily seen to be actually quantum compatible, sort of trivially. But there's lots of other classical reductions that are not quantum compatible. And the most notable and famous case of this are reductions that do something called rewinding. So rewinding is something that happens when you're analyzing the security of an interactive protocol. So you have an interactive adversary. And your reduction interacts with this adversary and basically runs it to some midway point in the protocol. And then saves the state of the adversary. And then runs the adversary from this point to the end of the protocol multiple times. And it's able to do that because it can always reset back to the state that it saved. So just to give you a picture, we can imagine we have a 3-message protocol between some prover and a verifier, and we're trying to prove soundness. So the reduction might interact with this malicious prover, record this first message of the prover, and then save the state at this point. And then run one execution of the protocol to the end, asking it a random challenge R, getting answer Z, recording this, and then rewinding it back, asking a fresh challenge R prime, getting a new answer Z prime, and recording this. And maybe it's going to use these transcripts of execution to break some hard problem. So the problem is that it's unclear how to rewind the adversary if it's quantum. Right? So the only thing quantum here is our attacker. The rest of the protocol is totally classical. And the problem is the security proof breaks down because we're assuming that we could rewind the adversary back to its original state. But if that internal state of the adversary is quantum, then that first execution, where we measured its answer Z, could irreversibly disturb its states. And so it's not clear how you go back and ask it more questions. Okay. So for the rest of this work, or for the rest of this talk, I'm going to think of rewinding as precisely this problem, where I have some interactive adversary, and I want to record a lot of responses from it. And just a brief disclaimer to clarify any potential confusion, rewinding is often, this is how rewinding is typically used to prove soundness of interactive protocols, but rewinding is also used to do things like prove zero knowledge, and this particular template of just recording lots of responses is not quite how it's used in zero knowledge. So for today, I'm going to think of rewinding as just record a lot of transcripts, and I'm thinking about applications for proving soundness. Okay, so with that out of the way, I'm going to focus the rest of this talk on Killian's succinct argument system, which is a really central and foundational result in cryptography that I think captures the full difficulty of this rewinding task. Okay, so what are succinct arguments? A succinct argument for NP considers a setting where you have a prover and a verifier. They've agreed on some statement, and the prover is trying to convince the verifier it's true. The prover also has a witness for the statement, so the prover could, of course, just send the witness over to the verifier. But the goal of a succinct argument is to do much, much better than that. You want to do something much more efficient. And so that's what succinct means. It means that the total communication of this protocol, along with the verifier efficiency, have only a polylogarithmic dependence on the size of the instance and the witness, instead of a linear dependence, along with the necessary polynomial dependence on the security parameter lambda. And in order to get this massive savings in efficiency, you have to sacrifice a little bit in terms of soundness. You no longer get perfect soundness. You have to settle for computational soundness. That's why it's called an argument. And this says that a malicious cheating prover cannot convince a verifier to accept on a false instance, except for the negligible probability. Okay, so in 1982, Killian showed how to construct a 4-message protocol, achieving succinct arguments for all of NP, assuming just collision-resistant hash functions, or CRHFs, which are a relatively mild assumption in cryptography. And it says that you have a hash function, it's very compressing, and it's hard to find 2 different inputs that hash to the same output. So this result has had a huge impact in crypto, both in theory and in practice. Okay, so despite the importance of this, we've had one flaw in the security of Killian's protocol. In particular, the security doesn't actually extend to the quantum setting. Basically, the canonical security proof for Killian's protocol runs into this issue with rewinding once you go to the quantum setting. In particular, the classical reduction for Killian rewinds the attacker an arbitrary polynomial number of times. And while we do have some techniques for rewinding quantum adversaries, they're actually fundamentally stuck at a far smaller, actually constant number of rewinds. So we had this big gap in what we knew how to do and what you actually need for Killian's protocol. So in this work, we resolved this problem. And actually, we give a slightly more general technique. So we show generally how to rewind a quantum attacker as many times as you want. So the big consequence of this is for the first time we can prove that Killian's protocol is post-quantum sound with a quantum binding CRHF. So all I mean is that the original classical protocol uses a standard collision-resistant hash function, and it turns out that in the quantum setting, you need to strengthen this definition a little bit of something called collapsing. This is the quantum generalization of collision resistance. So with that modification, it turns out that Killian's protocol is post-quantum sound. And more generally, using this technique, we can actually lift a really large class of soundness reductions to the quantum setting. Okay, so just to have something in mind, I'm going to recall Killian's protocol before I dive into what we actually do for rewinding. Okay, so in Killian's protocol, the high-level idea is that the verifier is going to get this massive savings in efficiency by essentially running a PCP check. But the one problem with that is that you don't want the prover to change the answers based on, or answer adaptively based on which positions of the PCP the verifier is interested in. So Killian's protocol solved this in this ingenious way by having the prover first commit to the PCP, and then later open the PCP on the positions that the verifier wants to see. So the way this works is the verifier samples a collision-resistant hash function H, sends it over to the prover, and then the prover basically hashes up the PCP in this tree. So it writes this PCP down at the leaves, and it builds this binary tree over the leaves where all the internal nodes of the tree are obtained by applying the hash to its two children, going all the way up to the root, and the root is the final commitment it sends over to the verifier. So this is a short commitment that's independent of the length of the PCP. And now the verifier simply runs a PCP check. So it samples random coins of the PCP verifier and sends it over to the prover. And that's going to specify some positions of the PCP the verifier wants to check. And so the prover simply has to reveal the value in these positions. But for every value it reveals, it also has to certify that it's opening it correctly, opening consistently with the commitment it sent in the second message. So for instance, if the prover needs to reveal the value of this black square, it's also going to have to reveal the values of all these blue squares on the root to leaf path. And the reason for this is that this is going to allow the verifier to basically hash its way back up the tree and check that this recomputes the root that the prover sent in the second message. Okay, so the verifier accepts if the PCP verifier accepts, along with all the openings being valid. Right, so the intuition certainly makes sense. Formally proving security, even in the classical setting, is a little bit delicate. And what you need to formalize is this idea that the collision-resistant hash function is somehow forcing the malicious prover to behave consistently with some fixed PCP string, because then you can appeal to the soundness of the underlying PCP. So the way we do it is by rewinding these last two messages many, many times. Right, so I'm just going to abstract away the details. I'm just going to think of the last two messages as a challenge R with an answer Z. And the goal is to record many accepting transcripts, RIZI. So accepting meaning that the verifier would accept in this whole interaction. And we're going to fix the choice of the first two messages this whole time. Okay. So what happens when you record many accepting transcripts? Well, one of two things is going to happen. Either all the transcripts that you record are going to be consistent with each other, meaning that if you see an opening to one position twice, it's always going to be the same value. But if that's the case, then you can actually piece together all your answers because they're basically revealing more and more of the PCP. So you can piece them all together and get a consistent PCP string. And what you're going to see is that this PCP is basically as good as the prover success probability. And that's going to be a contradiction because we're assuming it's a no instance. So there shouldn't be such a good PCP. So the only other option is that the answers are inconsistent with each other. But this simply is going to violate the property of collision resistance. The structure of the Merkle tree is going to assure us that anytime you have an inconsistency, you can find a collision. Okay, so this is the classical security proof. And now that we're going to move to the quantum setting, I'm going to zoom in on where all the action is happening, which is these last two messages here, right, where I repeatedly send a challenge R and then I get an answer Z. And at this point, the prover is a stateful prover, right? It has some state that is accumulated going into the last two messages of the protocol. And when this prover is quantum, this state acts as a quantum state. Okay, so let's look at the task. We basically want to play this challenge response game many, many times. And we have this initial guarantee on our stateful prover with state S. And the guarantee is that initially, it has some inverse polynomial, some noticeable chance of answering us correctly on a random challenge. Okay. So this is the probability over the randomness of R. And given one copy of this state, or access to a prover with this state, we want to generate many accepting transcripts. Right? So we have a p probability of getting an accepting transcript the very first time, but somehow we want to get a lot more transcripts than just one. Okay. And just to make sure things are making sense, remember this problem is totally trivial in the classical setting. We don't even bother to formalize this. Because when it's classical, when the state's classical, you just run many trials by copying the state or resetting it and running them all independently. Okay, but quantumly, we can't do that. We only have one copy of the states. And moreover, that very first trial is going to damage the state. Right? So measuring this answer Z could damage the state. And the reason that damaging the state is problematic is because you might have some initial success probability P, and then after that first trial, measuring that Z, perhaps the residual state corresponds to a prover who would only answer you correctly with some probability much, much smaller than P. So then how do you get more transcripts out of it? Okay, so the very, very high level idea of what we do is we devise a quantum procedure that we call a repair procedure, whose only function is to restore the prover's initial success probability. So all of the work in this paper is in designing this repair step, and the result of the repair step is that now you have a prover who has the same success probability as the prover did before you disturbed its state. So once you have this, you can run another classical trial, ask it a random question, disturb its state again, and then just repair it again. And so using this, you can lift these classical rewinding reductions to the quantum setting, so long as every time you query the adversary, you make sure to repair the state after the query. Okay, but notice that the state that I wrote the second time, this S1, is not the same as the state that I had the first time. And it turns out that initial state S could be irreversibly lost. But sort of the key insight here is that we don't actually need to recover the original adversary state. Right? The end goal to make this reduction work is you just need a lot of accepting transcripts. And so to guarantee that, you simply need to guarantee that every time you query the prover, it has a really good chance of answering you correctly. So what we're going to do is just try to repair the success probability, and we're not going to worry about repairing to the original state. Okay, so high-level overview of what the actual technique is. It's based on this alternating projectors idea. Oh, and sorry, before I go on, let me just say that when I talk about measuring the prover and doing a trial, I'm going to think of that as actually a binary outcome measurement. So actually the measurement is measuring its whole response, which could be polylogarithmically many bits. But I can actually appeal to the underlying crypto in the protocol, use the fact that it's actually opening this binding hash function. And by appealing to the crypto properties of the protocol, I can argue that from the prover's point of view, it looks like I just did a binary outcome measurement of whether or not the prover answered me correctly. I'm going to call this measurement pi r. It's the measurement corresponding to this challenge r. Okay, so the rough intuition for how our state repair works is we're going to identify the so-called good subspace. So pi p is going to be this projector onto a subspace of good prover states. So what is a good prover state? It's going to be a state that corresponds to a prover whose success probability is at least p. And I also want the guarantee that my initial prover is contained in this subspace. So for now, I'm going to take this as magic. I'm not going to say where it's coming from. But let's accept that we have this projector and that we can efficiently apply it. Then what could we do? Well, we're going to alternate two projective measurements until the measurement corresponding to pi p accepts. So we're going to alternate the measurement that disturbed the state, so the pi r measurement we applied that initially caused the disturbance, and we're going to alternate that with the projective measurement onto the good subspace. So what that looks like is that here we have the disturbed state S prime after applying this pi r to it, and we just alternate these measurements back and forth. And we're just going to keep going until the first time this pi p measurement accepts. Right? Because it's a projective measurement, we know that the residual state is going to be in the span of pi p. And by definition, we define this good subspace to consist of only states that correspond to good provers. Right? So the moment we're back in this good subspace, we have a prover whose success probability is at least p. Okay, so this is a bit of black magic. So let's try to make the details a little bit more precise. Like, why exactly does this work? Okay, so first off, how do we know this process even terminates? Right? What I said we're going to do is keep alternating these things back and forth until this pi p accepts. So how do we know that ever happens? Turns out this is fairly easy to show. You can actually prove a fairly general statement that says that if you have any quantum state that's initially in the span of one projector, and then you disturb it with some arbitrary other binary projective measurement, pi2, then you can always return to the span of the original projector by alternating pi1 and pi2 measurements back and forth, and it takes you expected constant number of times. So the way you prove this is you look at the two-dimensional case. It's not very hard in 2 dimensions. Turns out that for any angle between two like rank 1 projectors, you can show this is true, and then you can extend this to the general case using Jordan's lemma. Okay, so this part is actually easy. If we have this ideal projector, things will actually work. So then the real problem is, where does this projector come from? Why should there be an efficient projector onto good adversary states? Like, this seems to come out of nowhere. And in fact, I lied a little bit. We don't actually have such an efficient projector, and we don't believe that it's going to be possible to implement one. So how are we gonna plug this in? Like, how do we fill in this gap? What we're going to do instead is use a procedure of Marriott-Watrix that actually also uses the same alternating projectors idea. And we're going to use it to estimate the adversary success probability. And using this estimation procedure, we can implement something that roughly behaves like this pi p measurement does. Right? We wanted pi p to be this projective measurement that accepts if the adversary success probability is high. And what I'm saying is we have a procedure that approximately measures the success probability. And so we can simply approximate it and then output 1 if it's over p. Right? So we have this approximate version of pi p, and all of basically the technical crux of this work is showing that even if you have only an approximate way to recognize a subspace, this whole return to subspace idea still works. Unfortunately, I don't have time to go into the details, but I think the ideas underlying this proof are actually really cool. Okay, so this wraps up the technical overview of what we do. The key is basically showing this approximate implementation suffices to instantiate these alternating projectors. So let me just conclude by saying that the security of interactive protocols in the quantum setting has been sort of a long-standing open question because of the difficulty of rewinding. Right? This is the key technique for arguing about security in the classical setting, and it just totally falls apart in the quantum setting. And so we gave a general solution to this rewinding task for when you want to record many accepting answers from the adversary. And the way we do it is by repairing the adversary state after each invocation. And the next steps are, what other reductions can you lift to the quantum setting using this technique? And so some results along these lines, in a joint work with Alex Lombardi and Nick Spooner, we show that classical zero-knowledge protocols such as the graph non-isomorphism protocol of GMW86 remain secure against quantum attack. And in the wonderful work actually posted this week by Nir Batansky, Zvika Brakersky, and Yael Kalai, they use a rewinding technique to build post-quantum advice-preserving reductions, such as Goldreich-Levin and Regev's LWE search decision reduction. And they argue quite convincingly that advice-preserving is really the right notion of a cryptographic reduction. Right, thank you.
Some time for questions. So I have a question just on the last slide. Can you say more about this advice preserving? It's the first time I hear about it.
Oh yeah, so a common thing that happens when we talk about like non-interactive reductions is we say things like, well, if you have an adversary that has a state that breaks this thing, then I'm going to build some other adversary that's going to like break some other problem. But the question is like, what does it mean to build this other adversary? And typically, like when we have classical reductions that require like many copies of the adversary, we can say that, oh, like this list of the quantum setting, because I can just assume that like I have non-uniformly another adversary that has many copies of the state. Basically, it's another way to say advice preserving means uniform, meaning that I don't require multiple copies of the adversary. And since our assumptions are typically non-uniform anyway, people treat this as good enough. Like, oh, there exists some adversary for this. But typically, in crypto, you want a way to just transform an adversary into a way to break your assumption. You don't want to say that because I have an adversary, therefore, like non-uniformly, there exists some other adversary for my assumption.
I see.
So it's just it's qualitatively better, right? It's not just existence, but it gives an explicit way to construct the reduction.
Okay, let's thank Fermi again.